All right, so the next set of tests that we need to look at are comparison tests. And there's two different types of comparison tests. One is the direct comparison test, which we'll look at first, and the other is the limit comparison test. I've found that students tend to like the limit comparison test better than the direct comparison test just because of how you accomplish each one. Direct comparison test, we have to often prove inequalities, which I don't know, I think students don't have a huge amount of experience doing that up to this point, at least not for fairly difficult ones. Where the limit comparison test, you have to evaluate a limit, which we have a lot of experience over the past 2 semesters. So we'll start with the direct comparison test though first. So here's your direct comparison test. It says, all right, so let's look at two series where a sub n is less than or equal to b sub n for all n. So that means a sub 1 would be less than b sub 1, a sub 2 would be less than or equal to b sub 2, a sub 3 less than or equal to b sub 3, etc. So there's two statements here. They're both if-then statements, and we've talked about if-then statements previously. You can't read more into them than what they actually say. They only go in one direction. So here it says if b sub n, which is the bigger one, okay, the bigger series, converges, then a sub n converges. Okay. Remember, a sub 1 is less than or equal to b sub 1. A sub 2 is less than or equal to b sub 2. A sub 3 is less than or equal to b sub 3, etc. So if I add a1 plus a2 plus a3 plus a4, and I add b1 plus b2 plus b3 plus b4, etc. If I look at these two series, since each one of these is consecutively bigger than each one of these, then this sum should be bigger than this sum. Okay? So what was just said is that if this sum converges, which means this is equal to some finite value, and this one right here is smaller, well then by default this one also has to converge. Because in a way this is like the ceiling for this series here. That this one's going to be smaller than it, and since this one's finite, that doesn't allow this one to go to infinity because it's stuck below this finite value. So that's what this statement is saying here, which should, just with basic common sense, should make sense there. All right. Then the next one says, okay, let's look at these two series, but let's look at the other way. If a sub n diverges, then b sub n diverges. So now it says, okay, let's look at the smaller one. If this smaller one here diverges, okay, which means this thing is essentially going and getting bigger and bigger and bigger and bigger and bigger. Okay, it's going to infinity. As I keep adding and adding and adding, my sum is going to increase. And this one right here is bigger than this here. Well, if this thing's already infinite, it diverges, and this one's even bigger than that, then by default, this one also has to diverge as well. Okay? So that's what the comparison test says, which, again, should make sense here. If the bigger one is finite, then the smaller one should also be finite. It also says if the smaller one is infinite, then the bigger one should also be infinite. All right. So we can use that to determine convergence and divergence for some series here. Now, when it's all said and done, we're going to have a bunch of different tests we're looking at to determine convergence and divergence. Comparison test is oftentimes going to be one of the last things you look to do. But for right now, we're looking at these tests in these examples. So remember, we have a list of ones we've already worked with, and we could use any one of those to find whether or not this thing converges or diverges. So what do we have? We have the partial sum way of doing it, which I told you already, we're not really going to use a ton. That was just kind of a way to get started. It's oftentimes fairly difficult to do for a lot of series. Geometric series. This looks like it's close to a geometric series, but this plus here is the problem. If I didn't have this 2 plus 3 to the n, I just have 1 over 3 to the n, it would be geometric. But just a little bit of change here makes all the difference. Nth term, well, the problem is this thing goes to 0, so nth term won't apply. Integral test, not really something I really want to integrate, and it's not a p-series, so none of those really apply. So that's why we're going to look at the comparison test. Now, just like I said a second ago, this is really close to a geometric series. It's not, but it looks fairly close to it. So if I say, let's compare to the sum of n equals 1 to infinity of 1 over 3 to the n. Because that's pretty close to this one. I know that this one is geometric, where r is a third, because I could write this as 1/3 to the n. So if r is a third, that's less than 1. You have to go back and remember, okay, when r is less than 1, what does that mean? What that tells me is that this is going to converge. Okay. So if I'm trying to compare this to something that I already know converges, I have to show that this is smaller than this one, so that I can use this here. If b sub n converges, which we just found out, so let's call this one b sub n converges, then if I can show that this one is smaller, that a sub n is smaller than b sub n, then I can show that this one's also going to converge. So now what I have to do is I have to show that 1 over 2 plus 3 to the n is smaller than 1 over 3 to the n, or equal to, could also be the case, for n greater than or equal to 1, because that's where the series is starting here. Alright, well, if we look at this here, we could cross multiply. We would have 3 to the n is less than or equal to 2 plus 3 to the n. Is that true? Well, these are both the same. So if I add 2 to 3 to the n, does it get bigger than if I basically don't have anything added to it? Well, yeah, because this thing would be 0. I could say 0 is less than or equal to 2. I'm adding 0 to this one. I'm adding 2 to this one. Since I'm adding more on this side, then clearly this is bigger. And if this is bigger on this side, then that follows that this one is smaller. Essentially saying if the denominator here is bigger than this denominator with the numerators being the same, then this fraction is going to be smaller. So is this true? Yes. So therefore, by the direct comparison test, I'll abbreviate it DCT, the sum of 1 over 2 plus 3 to the n also converges. Alright, we're going to try and do the same thing again here with this one. We'll see if we can compare it to something. Now again, we could run through our whole list of things that we have, and we don't have to jump right into comparison tests. But we're doing that now just simply because we're looking at getting practice at that. But honestly, if we go through all our list of things we could do, none of them are going to work that well. So what I'm going to do is I'm going to say, well, this looks fairly close to a p-series. So why don't I say, let's compare to 1 over square root of n, which is the same thing as 1 over n to the 1/2, which is a p-series. Specifically, it's a p-series where p is a half. So you'd have to then remember what happens for a p-series when p is a half. That's less than 1. Well, that diverges. All right, so now we have a divergent series. Well, if we know that this thing diverges, and we're trying to figure out what happens to this, well, the only way we can use this series to help us figure out what happens to this is we have to show that this one is bigger. So we would need to show that 1 over 2 plus the square root of n is bigger than or equal to 1 over the square root of n. Now there's a problem there. The problem there is it's not bigger. Okay? Again, if you went cross multiplied, you'd have the square root of n is less than or equal to 2 plus the square root of n, very similar to the last example. And this is not true. I can't add 2 to the square root of n and have it be smaller than square root of n itself. So that's not true. Well, if that's not true, what does that say? Well, it actually says nothing. Okay? It doesn't say anything. It just says, well, this was not the right series to compare it to. All right, well, what do we do now? Well, we got to find something else to compare it to. Well, this was the most obvious one to try and compare it to because this and this don't look all that different. But it just didn't work with the comparison test. Now, here's where you're going to have to start getting some instincts as to what you think is going on with this series. So you got to ask yourself, looking at this series right here, and knowing that this one diverges, do you think that adding 2 into this denominator is going to all of a sudden change this series here by adding 2 to it, which is the only difference of this one versus this one? Do you think adding 2 to the denominator is really going to affect it diverging or converging? Do you think it's going to change it from something that diverges to something that converges? And usually the answer to that question is no, it's probably not going to make that big a difference. So your instinct should be that, well, if I know that this one over here diverges, this one probably still diverges. I just need to show it. So what am I going to do? I got to compare it to something, but I got to compare it to something that does the same thing that I think is happening with this one. So I need to find another series that I'm going to compare it to that diverges. I also don't want it to be that different than this series, because if it's different from this series, it's going to be hard to prove this inequality that we have to show. So you want to try and keep it fairly similar. This is the problem with the comparison test, is you need to just pull these series out of thin air. There's no specific way I can tell you this is how you come up with the series you're going to compare to. First, you try and do something that's similar to it like we did, but that doesn't always work. So let's say we're going to compare it to something fairly easy. This is similar to a p-series, so I want to use another p-series. One of the simplest p-series that diverges is the harmonic, 1 over n. So this is a harmonic. It's p-series, where p equals 1. It diverges. So we know this information. If we're going to compare to the one we're looking for here, then we have to show that 1 over n is bigger than or equal to, I didn't equal it the wrong way. I have to show that 1 over n is smaller than 1 over 2 plus the square root of n. So if this is smaller than this one, and this one diverges, then by default this one's going to have to diverge. Alright, so is this true? Well, we can do the same thing. Let's cross multiply here, which as long as things are positive, it's fine. We don't have to worry about flipping the sign around. So we get we get 2 plus the square root of n is less than or equal to n. That's not as obvious to see necessarily, so we need to work with this a little bit. And this is again the problem with the direct comparison test, is we got to prove these inequalities are true or not true, which is something I don't know that a lot of people have a ton of experience with up to this point. So let's keep going. I'll move the 2 over to that side because I think getting rid of the square root could be helpful. So square root of n is less than or equal to n minus 2. If I square both sides, this side just becomes n. If I square the other side, I'd have n squared minus 4n plus 4. If I then move this n over here, I get 0 is less than or equal to n squared. I'd have to subtract it, so what do we get? Minus 5n plus 4. And the question is that true? Is this bigger than or equal to 0? Well, the problem is not always. But is there some n for which it is true for that n and up? So that n greater than or equal to some number. Is there some value that I can use where this is true, and from that value all the way to infinity, this works? Well, I think we could answer to that and say yes, because we know this is a parabola. And so a parabola has the shape that looks like that. And whether a function is greater than or less than 0 depends on whether it's below or above the x-axis. Well, there's a possibility that this parabola could dip below the x-axis, in which case, for these x's here, the polynomial, or the parabola, would be less than 0. But there definitely should be some x value, or n value, whatever you want to call it, that from that point on, we will continue to be positive and be positive the whole way. So is this true? Yeah, for certain n values. Now, the way we could figure that out is to figure out, well, where is it equal to 0? That's pretty easy if we factor it. If we factor it and say, all right, n, minus 4, n minus 1, that would give me n is 4 and n is 1. So that means this is 1 and this is 4 are the two x-intercepts, or in this case, the n-intercepts, whatever. So between 1 and 4, if I plugged, like, say, I don't know, 2 in for n here, I would get a negative answer. And I would get something that's less than 0, not greater than 0. But once I hit 4 and I go past 4, all those n's will continue to get me positive values and continue to give me positive values, and this will be true. So, long story short, this is true for n greater than or equal to 4. Now this series says it starts at 1. Well, it doesn't really matter. Something I said a while ago was that if we're determining whether or not a series converges or diverges, where that series starts, whether it starts at 1 or 2 or 3 or even 4, doesn't really affect whether or not the series will converge or will diverge. It will only affect what the series converges to if it were to converge. But it doesn't change the fact that it's going to converge or diverge. Because all you're doing is adding or subtracting a few finite amount of terms. So if something is already finite and you just subtract off a couple of terms from that, it's still going to be finite. Or if a series goes to infinity, if it diverges and it just keeps getting bigger and bigger and bigger, if you just don't add the first 3 terms to that series, that's not really going to change the fact that it's going to infinity. Okay? So the fact that as long as this works at some point, this inequality holds, so then this is true at some point, then we can use this comparison test. But again, here's the downfall with the comparison test, the direct comparison test, is this inequality business is not an easy thing to do. So anyway, let's finish this off. So we could say by the direct comparison test, the sum of 1 over 2 plus the square root of n also converges. That's the exact opposite of what we just said. Also diverges. Okay. And so if it diverges for n 4 to infinity, it should also diverge from n of 1 to infinity. Okay. All right, so you saw that the direct comparison test can be fairly complicated, which is where then the limit comparison test comes into play. And honestly, it doesn't really matter which one you use. Oftentimes it's easier to use the limit comparison test just because you're more comfortable with it, but I don't know that it really matters either way. There are very few examples where you could say, well, you're better off using the direct comparison test as opposed to the limit comparison test. So let's look at the test. First off, there's too much going on here. I have too many a sub n's and b sub n's, so let me erase this. All right. So let's pretend that was never there. All right. So what it says is, suppose a sub n is positive and b sub n is positive. That's it. Doesn't matter which one's bigger than the other one. We don't have to prove any type of inequality. Just a sub n is greater than 0 and b sub n is greater than 0. And the limit as, this is supposed to be an n, goes to infinity. Let me erase this. Oh, goodness. The limit as n goes to infinity of a sub n over b sub n equals L, where L is a finite positive number. So it says, take a sub n and take b sub n and divide them, and then do the limit of that quotient as n goes to infinity. If L ends up being a finite positive value, then the sum of a sub n and the sum of b sub n both do the same thing. They either both converge or they both diverge. Okay? So in this case, you don't have to prove that one is bigger than the other. You just have to show that the limit of the quotient is a finite positive value. Now, there's some reason behind this, and it has to do with what we've learned about limits along the way. One thing I've talked about with limits is the limit as n goes to infinity of some quotient. Okay? Think of this as just a regular old quotient, a sub n over b sub n. We talked about how there's basically three different versions of this limit as n goes to infinity. One is we get 0. We would get 0 if the denominator is growing faster than the numerator. Okay. Another option is infinity. And that would happen if the numerator is growing faster than the denominator. And the third option is we get some finite value. And that would happen if these both are growing at the same rate. Okay. And so we've discussed this. You've discussed this all the way back into pre-calc when you talked about horizontal asymptotes of rational functions. It's the same exact concept. So what this says is that if we get some finite positive value, okay, not this scenario, but this scenario, then we can say that both series are doing the same thing. Why? Because the terms are growing at the same rate. Okay, remember, we said the numerator and denominator would be growing at the same rate to be able to get this option. So the terms of a sub n, if a sub n is actually the terms of this series, and b sub n represents the terms of this series, we're basically saying that the terms of each series are growing at the same rate. And if they're growing at the same rate, then they should both do the same thing. That's why this limit comparison test works. Now that's really the kind of the rough, I wouldn't even say proof of the test. That explains a little bit as to why the test is saying what it is. Okay? So, if I look at this right here, this is what we call the general harmonic series. And I need to show that it converges. If I compare it to the harmonic series, which I know diverges, right? This is harmonic. It diverges. And rather than do some sort of inequality like we did before, if I do the limit as n goes to infinity of 1 over an plus b over 1 over n. This divided by this. It doesn't really actually matter the order. I could do this one divided by that one. All right, a and b being just two constants, positive constants. Look at what happens here. If I do this limit, fraction divided by fraction, I flip and multiply, I get the limit as n goes to infinity of n over an plus b. N's going to infinity. Remember, a and b are just constants. Well, I have the same power here and here. These are going to grow at the same rate. So my limit should be 1 over a. Since a is a positive constant, this is a finite positive value. And therefore, by the limit comparison test, which I'll abbreviate LCT, the sum of 1 over an plus b also diverges. Okay. Let's go back to the one we just did a second ago. The sum of 1 over 2 plus the square root of n. Okay. And we said that that one diverged, but we did with direct comparison test. Well, let's do a limit comparison test. Let's compare it to the sum of 1 over the square root of n, which is not very different than that. And this time we can do this. With direct comparison test, it didn't work out very well for us. But here with limit comparison test, we can. Remember, this thing diverges because it's p series. P is a half, which is less than 1. So if I then do the limit as n goes to infinity of 1 over 2 plus the square root of n divided by 1 over the square root of n, I would get the limit as n goes to infinity of square root of n over 2 plus the square root of n, because why? I have a fraction divided by fraction, flip and multiply. Now if n goes to infinity, look at this, the square root of n over square root of n, they're the same function, they're growing at the same rate, same powers. What would I get here? 1. Well, if I would get 1, isn't that a finite positive value? Yes, since it is, then by limit comparison test, the sum of 1 over 2 plus the square root of n also diverges. So you see, limit comparison test does make things a heck of a lot easier. What if I gave you this example and I said, tell me what happens to this series. The sum of n equals 1 to infinity of 1 over 5n squared plus 2n minus 1. So again, looking at it, you go, okay, well, if I can find something that I can compare it to so that when I do the limit as n goes to infinity of this divided by whatever this other series is, that I'm going to get this finite positive value, that I'm going to have this idea that the numerator and denominator are going to grow at the same rate, then that's the series that'll work with limit comparison test. Well, think about it. If I compare to the sum of 1 over n squared, again, that's a p series. Very easy. P is 2. That's greater than 1. And when the power is when p is greater than 1, we say that it converges. So if I compare this to 1 over n squared, this thing converges. If I can make sure that this limit gives me a finite positive value, then I can say that this series converges. Well, again, fraction divided by fraction. So I have the limit as n goes to infinity of a flip and multiply. So I get n squared over 5n squared plus 2n minus 1. As n goes to infinity, same degree, top and bottom. So the limit should be 1 over 5. If you don't like that, we could always use L'Hopital's rule. As n goes to infinity, this thing's going to go to infinity. This is going to go to infinity. Take the derivative top and bottom. You're going to have to do it a couple times. Either way, you're going to get 1/5. That's a finite positive value, right? So by limit comparison test, the sum of 1 over 5n squared plus 2n minus 1 also converges. Now we can't say what it converges to, but at least we know it converges. So you see how this limit comparison test can really, really be helpful. And I think definitely easier to work with than the direct comparison test, simply because you should be more comfortable in doing limits than you are in proving inequalities just because of your experience or lack thereof. Okay, so here's another one. We want to show that this thing converges or diverges. It's getting a little more complicated now, but remember, I want to do a limit as n goes to infinity of this square root of n over n squared plus 1 divided by something so that I get that finite positive value, so that this grows at the same rate as that. Now most likely this is going to be a fraction, so then I'm going to have to flip and multiply up to here. But I want the numerator and denominator to eventually get the same degree. And if the numerator and denominator are the same degree, like if I get an n cubed over an n cubed, or an n squared over an n squared, I can just look at the leading coefficients here to be able to come up with my answer for my limit. So thinking of that, that should tell you what series you should compare to. So let's say we want to compare to the sum of, now take a second to think about it. What would you compare to so that you can get the computation here to work out the way you want it to get that finite positive value? So hopefully you came up with it, and it would be 1 over n to the 3 halves. This is a p series. P is 3 halves. That's bigger than 1. When it's bigger than 1, it converges. So you got to remember this information about p series and geometric series, etc. Oftentimes we try and compare it to either p series or geometric series because those are really easy series to know what happens to them. R greater than or less than 1 for geometric series, p greater than or less than or equal to 1 t series. You know exactly what's going to happen. So we try and use either of those. All right, so then what I'm going to do is if this is what I'm going to compare to, then this 1 over n to the 3 halves would go here. We'd flip and multiply. So we end up with the limit as n goes to infinity of n to the 1 half times n to the 3 halves over n squared plus 1 because I have to flip and multiply. Well, this is going to give me n squared. So I have the limit as n goes to infinity of n squared over n squared plus 1, which just equals 1. Finite positive. Therefore, by limit comparison test, LCT, the sum of the square root of n over n squared plus 1 also does the same thing that this one does, converges. All right, here's one more. This one is definitely far more difficult than some of the other ones, but you have to think about if I'm going to use the limit comparison test on this. And I would use the limit comparison test because honestly nothing else is going to work. It's not geometric. Nth term test. Well, we could use nth term test directly on this thing. It's going to apply. But nth term test, integral test, p series, direct comparison, limit comparison. These are all the different tests we have. So a couple of things here. One, I could just use nth term test, right? nth term test says I don't have to take the limit of a quotient. I just take the limit as n goes to infinity of the series itself. And see what happens to that. And if that doesn't equal 0, as long as that doesn't equal 0, then I can say diverge. Whereas the limit comparison test says I'm going to do the limit as n goes to infinity of the series divided by some other series, and I want to get a finite positive value out of that. But let's look at this one first. Okay? As n goes to infinity, this numerator is going to get big, this denominator is going to get big, so they're both going to infinity, so I could use L'Hopital's rule. And if I use L'Hopital's rule, the limit as n goes to infinity of the derivative of the numerator, I need product rule to do that. So that would be 2 to the n plus n 2 to the n ln of 2 over 12n squared. As n goes to infinity, the numerator is still going to go to infinity, the denominator is still going to go to infinity, so I can do L'Hopital's rule again. So the limit as n goes to infinity of 2 to the n ln of 2, that's the derivative of this, plus take the derivative of this, I'm going to have to do product rule again, so that'll be 2 to the n ln of 2 plus n 2 to the n ln of 2 squared all over 24n. And I think you kind of see a pattern here. I'm going to have to do L'Hopital's rule again because this thing's going to go to infinity over infinity again. But this numerator is just going to keep getting bigger and bigger and bigger every time I take the derivative. And this thing eventually is going to go away, or at least just become a constant. And so one more step of L'Hopital's rule, you get derivative of the numerator, which, you're going to get a bunch of things with n's. You're going to get 2 to the n ln of 2 squared plus 2 to the n ln of 2 squared plus 2 to the n ln of 2 squared plus n 2 to the n ln of 2 cubed. Let's just take the derivative of each one of these pieces over and over again. In the bottom, you're going to get 24. Now, as n goes to infinity, the denominator is just 24, but the numerator is going to keep getting bigger and bigger and bigger. Well, if the numerator gets bigger and the denominator stays 24, what do we get? We get infinity from that limit, which is not 0. Remember, the whole point is you're trying to not get 0. So what this tells me is that the terms themselves, the individual terms of this series, are going to infinity. The terms are getting bigger and bigger and bigger and bigger as I go. And there's no way that can converge if the terms are getting bigger. It's like saying 1 plus 2 plus 3 plus 4 plus 5. Okay? Those terms are getting bigger. As I keep adding, you should assume that the sum is going to keep getting bigger and bigger and bigger and bigger. It goes to infinity. So, by nth term test, nth term test, it diverges. Okay? But let's look at it in comparison test, specifically limit comparison test, just for a second. Our list of different tests that we're learning is increasing by the day. And so there's going to be series where there are multiple things we can do to it to determine whether or not it converges or diverges. So this one right here, nth term test, works. Limit comparison test could also work. So let me just get rid of all this for a second. Okay. So let's say I want to compare to, now remember, we got to think of something that's going to divide by this by so that the numerator and denominator grow at the same rate. So let's see, if I can get an extra n squared up here so that this turns into an n cubed to match up with that. Okay. Actually, no. Here, remember, if I divide by this fraction, I'm going to flip this and multiply. So the n squared actually has to be in the bottom so that it multiplies up here. And then if I have a 2 to the n up here to come down into the denominator of this one to match up with the 2 to the n, then this would be the series that should work. The problem is, this isn't any specific type of series. Say 1 to infinity. It's not any specific type of series that you could say, oh, well, this converges because it's P series, converges because it's geometric series. So you just have to figure out what happens to this. Well, you could do nth term test. This thing, so you could say diverges by nth term. Why? Because if you do the limit as n goes to infinity of 2 to the n over n squared, that's going to be infinite. For, think about what we said, 2 to the n is going to grow faster than n squared. We could show that by L'Hopital's rule, but 2 to the n grows faster than n squared, numerator goes faster than denominator, so you're going to get infinity as your answer. So that's not 0, and that's why nth term test applies. So then if I said, all right, let's do the limit as n goes to infinity of n 2 to the n over 4n cubed plus 1 divided by 2 to the n over n squared, I have the limit as n goes to infinity of flip and multiply n cubed 2 to the n over 2 to the n times 4n cubed plus 1. So thinking about numerator and denominator now, you have an n cubed 2 to the n, you have an n cubed 2 to the n. They're going to grow at the same rate. So if I divide the leading coefficients, 1 and 4, that should be the answer I get here, which is a finite positive value. So because I got a finite positive value from the quotient that I did with the limit of, then both should behave the same way. Remember, this thing diverges. So then by limit comparison tests, the sum of n 2 to the n over 4n cubed plus 1 also diverges. Okay? So, you could use multiple tests to do this. Sometimes we would do it this way instead of what I just went straight to the nth term test in the beginning. We do it this way because this one is easier to prove with the nth term test than maybe this whole thing was. And then when you do the limit of the quotient, it's pretty easy to see that you're going to get 1/4. So maybe computationally, the limit comparison test is easier. But they're basically doing the same thing. So as the number of tests we have increases, there's going to be more ways to show that something converges or diverges. And one person might use one, another person might use another, and yet you're still going to get the same result in the end. What you can't have happen is one person used the nth term test and shows that something diverges, and then someone uses, say, the limit comparison test and says that that exact same series also converges. That can't happen. You can't have a series both converge and diverge. So one of those has to be wrong. So even though there might be multiple ways to do something, they should still end in the same result. Either always telling you that the series converges or always telling you that the series diverges.